Welcome to the new session in physics. Today we are discussing the topic diffraction from the chapter Wave Optics. What is diffraction? When parallel waves of light are obstructed by a very small object, that is sharp edge, slit, wire, etc., the waves spread around the edges of the obstruction and interfere, resulting in the pattern of dark and light fringes. When light diffracts off of the edge of an object, it creates a pattern of light referred to as diffraction pattern. If monochromatic light source such as laser is used to observe diffraction, below are some examples of diffraction patterns that are created by certain objects. As you can see, we have first one as sharp edge of a razor blade, and you can see the diffraction pattern when laser beam is used. Then comes the slit. Third one is for wire, and fourth one is for a circular hole. So on comparison, we can see that in the case of circular hole, the diffraction pattern obtained is circular in shape. So actually diffraction, it is the bending of light at the sharp corners of obstacles. Diffraction of light occurs when the size of obstacle is comparable to the wavelength of light. All types of waves, light waves, sound waves, matter waves, and waves on water, etc., shows diffraction. And the finite resolution of our eye or of optical instruments such as telescope or microscope is limited due to the phenomenon of diffraction. In Young's double slit experiment, Thomas Young replaced the two slits by a single slit, and that experiment is referred to as Young's single slit experiment. When the light passed through one slit, a different type of pattern was observed on the screen. The pattern which was observed had a central maximum which was very wide as compared to the interference pattern, and there were alternate dark and bright bands, and their intensity was decreasing on both sides. The central maxima was very wide, whereas the corresponding secondary maxima and minima were reduced in intensity. Now let's discuss diffraction and the single slit diffraction pattern in detail. It is a common practice that when a music player works in our home, the sound will reach our ears even if we can't see the music player. It is because of the fact that sound waves, they can bend around the obstacles in its path and it can reach our ears. This property of bending around obstacles is common for all the waves, all the types of waves including light waves. Now let us see this diffraction in the case of water waves at a slit. If the slit has more width, we can see that the effects of diffraction or the spreading due to diffraction is less. The narrower the slit becomes, the spread or the bending due to diffraction, it increases. It is very clear from this. Smaller the size of the slit or obstacle, larger will be the effect of diffraction. Or in other words, we can say that the size of the obstacle should be comparable with the wavelength of waves for diffraction effects to be observable. Diffraction is applicable also for light waves. Light waves, as we know, its wavelength, it ranges from 400 nanometer to 800 nanometer. So usually diffraction effects are not observable since most of the obstacles, they have their sizes much more than the wavelength of light. Consider an obstacle kept in the path of light from a point source. Light travels in straight line and it falls on a screen placed at a distance. On the screen, as we expect, it forms a shadow as the obstacle is kept, but the boundary between the illuminated region and the shadow region is not clearly defined. At that boundary, we can see alternate bright and dark bands, and this pattern, it is called as diffraction pattern. Now let us consider the diffraction at a narrow slit. On either side of the narrow slit, we are keeping one source of light and a screen. The source of light is a monochromatic source of light. The monochromatic light falling on the narrow slit, it produces the diffraction pattern on the screen, which consists of a central bright region, and on either sides it has alternate bright and dark regions. But the intensities of the bright regions, they fall off very rapidly on either side of the central bright region. Now let us see how can we explain this diffraction pattern due to a narrow slit. Now let the width of the slit be A, that is Ln is equal to A. Now the source and screen are kept at far away distance from the slit, so that the light coming from the source can be assumed to be parallel rays and the wavefront can be assumed to be plane wavefront. That means when the incident waves they strike on the slit, the wavefront is assumed to be plane wavefront, and according to Hygiene's principle, all the points on the wavefront act as the source of secondary wavelets, and these secondary wavelets will propagate in all directions with the speed of propagation of wave, and it is due to the interference of the diffracted waves coming from these secondary wavelets. The diffraction pattern is formed at a screen which is kept at far distance from the slit, and as you can see, the diffraction pattern consists of central bright region and followed by the alternate bright and dark regions on either side. Now, since the screen is kept at large distance, the rays coming from the slit onto the screen can be assumed to be parallel to each other. Let us consider a diffracted beam of light moving towards a point P on the screen. Now for the slit, the width is A, and suppose this diffracted beam makes an angle theta with the straight direction. That means the angle of diffraction here, it is theta. To state whether the point P appears bright or dark, or to say whether at the point P constructive or destructive interference takes place, we should obtain the path length difference between the waves when they reach at the point P. For that, let's consider two waves starting from the 2 points L and N, which are the boundary points of the slit, which are at a distance A. So when the waves reach at the point P, the path length difference between the two waves will be NP minus LP, which is equal to NQ. Now from the figure, if we take sin theta will be equal to NQ divided by Ln. Here Ln is nothing but the slit width of the slit, which is represented by A. Therefore, NQ will get as A sin theta. Now, for small angles of diffraction, by small angle approximation, sin theta will be approximately theta. Therefore, the path length difference, it becomes A theta. Hence, to conclude, between the two waves which start from 2 points separated by a distance A, the path length difference when they reach the point P is A theta. So, speaking generally, from 2 points which are at a separation Y, if two waves start and when they reach the point P, the path length difference between them will be Y theta. So that point can be generalized. Now it is this A theta which decides whether the point P will appear as bright or dark. The single slit diffraction pattern, it consists of a central maximum, and the position of central maximum is at A theta equal to 0 or theta equal to 0. That is, on the screen it is at C. Now, the secondary minima are observed at a theta equal to plus or minus n lambda or theta equal to plus or minus n lambda by a, where n can have values like 1, 2, 3, etc. So, on either side of central maximum at these positions, that is theta equal to plus or minus n lambda by a, we can observe secondary minima. And the positions of secondary maxima are given by a theta equal to plus or minus n plus half lambda or theta equal to plus or minus n plus half lambda by a, where n can take values like 1, 2, 3, etc. So here plus or minus, in these two conditions, plus or minus stands for on either direction. That means on either directions of central maximum, equidistant points, at equidistant positions we have secondary minima and secondary maxima. The intensity distribution of diffraction pattern is as shown. So you can see a high intense one, that is central maximum, that is at theta equal to 0. Here along x-axis it is theta and along y-axis it is intensity. So at theta equal to 0 you have the maximum intensity which corresponds to the central maximum, and the first minimum they are at lambda by a and minus lambda by a. The second minimum at 2 lambda by a and minus 2 lambda by a. Now, the first secondary maximum, it is at 3 by 2 lambda by a, and on this side it is at minus 3 by 2 lambda by a. And the second secondary maximum, it is at 5 by 2 lambda by a and minus 5 by 2 lambda by a. So, as the figure suggests, it means that the secondary maxima are of decreased intensity compared to the intensity of central maximum. The secondary maxima are having reduced intensity and their intensities are getting decreased gradually. Now let's explain how the central maximum, secondary minima and secondary maxima are formed. The actual explanation for the formation is beyond the scope of our syllabus. So we will explain in a somewhat convincing way. Now in the diffraction pattern due to a single slit, a central maximum is obtained at C. At C, the path difference between the rays coming from LM and MN is 0. Hence, constructive interference takes place and that point is found to be central maximum. It is also called as principal maximum. Since the light rays from different points of the slit interfere constructively, that point C is becoming maximum bright. In the case of secondary minima, how the intensity become minimum or how it becomes a dark region, we are explaining that. For that, we take the position of first secondary minimum. That we will get from the positions of secondary minima, that is theta equal to plus or minus n lambda by a. So for first secondary minimum, n will be equal to 1 and we get theta equal to plus or minus lambda by a. Now to explain how this is formed, we will assume the slit to be divided into two equal parts. So in this diagram, Ln stands for the slit whose width is A. Now we assume that Ln is divided into two equal portions, Lm and Mn. So the width of those two portions will be A by 2. Now consider two waves starting from the points L and M. Now the separation between L and M is A by 2. Now in the previous discussion we have already concluded that if two waves start from two positions which are at a distance y, then the path difference between those two waves when they reach a point P is given by y theta. So if the waves start from two points A and B, we will take such that A and B are separated by a distance y. So from these 2 points waves are going, and when they reach at a point P, what will be the path length difference between those two waves? It is given by y theta. So using that logic, here the path length difference between the waves from L and M when they reach the point P is given by A by 2 theta. So here theta we already obtained, theta is lambda by A. So we have A by 2 into lambda by A, that is equal to lambda by 2. That means path difference is equal to lambda by 2. Path difference between the waves from L and M when they reach the point P is lambda by 2. So we know if the path difference between two waves reaching at a point is lambda by 2, the two waves will undergo destructive interference. Okay, so the two waves from L and M will undergo destructive interference. Now you can assume another point just below L and just below M, so that their separation is A by 2. So if we assume the two waves to be starting from these 2 points and reaching at the point P, between those two waves also the path length difference will be lambda by 2. Those waves also will get destructively interfered. That means for all the points in the upper half LM, there will be a corresponding point in the lower half MN such that the separation is A by 2. So the waves from such 2 points which are at a separation A by 2 will undergo destructive interference when they reach the point P. That means all the waves from the upper half LM is getting destructively interfered by the waves from the lower half LN. Okay, that means all the waves get destructively interfered and the point P appears to be dark. So this is how first minimum we can explain. Now in the case of second minimum we obtain at theta equal to plus or minus 2 lambda by A. So we assume the slit to be divided into 4 equal parts. So each part is having a width A by 4. Okay, now consider 2 nearby 1/4 parts. That means here I call it as L dash, then this as M dash, and this is M. So consider the portion L dash and L dash M dash. So we will take L and L dash. If we assume two waves to be starting from L and L dash, when they reach the point P, the path length difference between the two waves when they reach the point P is A by 4 theta. So here theta is 2 lambda by A. So we get, substituting for theta, we get the path difference to be lambda by 2. If the path difference between the two waves is lambda by 2, again destructive interference will take place. That means the wave from L is getting destructively interfered by the wave from L dash. By the same argument, we can say that all the waves from L dash, okay, from this L dash will get destructively interfered by the waves from L dash M dash. Because for all the points in L dash, there will be a corresponding point in L dash M dash for which the separation is A by 4. So all the waves from L dash get destructively interfered by the waves from L dash M dash. In the same way, if we consider waves from M dash and N, not N, M dash and M. So the separation also, here also the separation is A by 4. So for those waves also path difference is lambda by 2 and those waves will undergo destructive interference. Okay, that means all the waves from M dash M is destructively interfered by the waves from Mn. Okay, so the thing is this, from all the parts of the slit, the waves are getting destructively interfered. First two quarters get destructively interfered. The last two quarters also get destructively interfered. That means again the point P appears to be dark, and that's what we call as second minimum. So this is how we can explain the occurrence of secondary minima in the diffraction pattern. Now let's see how can we explain the occurrence of secondary maxima. As we said, secondary maxima are observed at positions theta equal to plus or minus n plus half lambda by a. So for first secondary maximum, we can keep n equal to 1 and we'll get theta equal to 3 by 2 lambda by a. So to explain the secondary maximum, we assume the slit to be divided into 3 equal parts. So each part is having a width a by 3. Okay, now consider the 2 points L and L dash on the slit. Now if we assume 2 waves to be starting from the points L and L dash, the secondary wavelets, when they reach the point P, the path difference between those two waves will be a by 3 theta. So substituting for theta, we get lambda by 2. The path difference between those two waves which starts from L and L dash is lambda by 2, which means that those two waves will get destructively interfered. So by the same argument, all the waves from L dash will get destructively interfered by the waves from L dash N dash, because for all points on L dash, there will be a corresponding point in L dash N dash for which the separation is a by 3. So all the waves from the first two 1/3 portions will get destructively interfered. But what about the waves from N dash, N dash? They will not undergo any destructive interference and they constitute towards the brightness at that point P. Okay, so if this condition, that means at the positions where theta equal to 3 by 2 lambda by a, 1/3 of the slit will be contributing towards the intensity. So that portion appears as a bright region, but the intensity of light will be very less compared to the central maximum. So that is how we can explain the position of first secondary maximum. Now coming to second secondary maximum. So it is observed at n equal to 2. So theta we will have 5 by 2 lambda by a. So we will assume the slit to be divided into 5 equal parts. So each part is having a width a by 5. Now if we consider two waves starting from L and L dash, when they reach a far distant point P, the path difference between the two waves will be a by 5 into theta, that is lambda by 2. So as we stated earlier, these two waves, that means the waves starting from L and L dash, will get destructively interfered. Not only that, all the waves from this portion will get destructively interfered by the waves from this portion. Okay, similarly, the waves from this 1/5 portion will get destructively interfered by this portion. So all the 4 portions, the waves, they get destructively interfered and only 1/5 of the slit is remaining without destructive interference, that is N dash N. So that much portion of the slit contribute towards the brightness at that point. So that point appears as bright, but its intensity will be still lesser than the first secondary maximum. So this is how we can explain the occurrence of second secondary maximum. In the case of third secondary maximum, we can assume the slit to be divided into 7 equal parts. So only 1/7 of the slit will be contributing towards the intensity. So this is how we can explain how the intensity of secondary maxima decreases and how it gets varied from the intensity of central maximum. Now the width of central maximum. So we have already discussed all the fringes, all the bands, they are not of equal width and not of equal intensity. The width and intensity of diffraction fringes are different. Okay, so the central maximum is the broadest one or the widest one. So we mention only the width of central maximum. So in interference pattern we were discussing fringe width, but in diffraction pattern we mention the width of central maximum. So what will be the width of central maximum? In diffraction pattern we were mentioning the positions of fringes as angular positions. So the linear width of central maximum, that is equal to angular width into distance of the screen. Means angular width, we can explain the angular width from this graph. And what do you mean by distance of the screen? Distance of the screen from the slit. So at what distance the screen is kept from the slit, that's what we mean by distance of the screen. We assume that distance to be capital letter D. Now let's discuss what is the angular width of this central maximum. You know, this is the central maximum, and the width of angular width of central maximum, we can say that it is the angular separation between the first secondary minima on either side. Okay, the angular separation between the first secondary minima on either side, that gives the angular width of central maximum. So first secondary minima, they are located at lambda by a and minus lambda by a. So the width becomes the angular width or the angular separation between the first secondary minima, that is lambda by a minus lambda by a. So that separation, it becomes 2 lambda by a. So the angular width is what? 2 lambda by a, that multiplied by the distance of the screen will give us the actual width of central maximum. So here the width of central maximum is 2 lambda d by a, where lambda is the wavelength of light used, d is the distance of the screen from the slit, and a is the width of the slit. So with that we conclude today's lesson. Thank you.